Good day, ladies and gentlemen, and you're very welcome to the Chappelle Natural Philosophy Society's alternative talks, as we call them. We hold these talks every fortnight where we go into some detail in regard to some research which has been done in fundamental problems in physics, mainly from an alternative point of view, but not necessarily so. On the other Saturdays, we actually have a more general talk about fundamental problems in dissident physics. For example, recently we were looking at how we might best address the general audience of people. Had we a limited time, or had we maybe some publication to deliver to them, with regard to highlighting some aspects of contemporary physics where we feel that the mainstream have gone somewhat astray. Now, first of all, I must apologize today for a slight mix-up in that there was a delay in announcing today's meeting. In fact, it wasn't really announced until I did it about an hour ago. However, I have started because I am cognizant of the fact that we have social media participants, Facebook and YouTube people coming in, and I hope people are there. There's nobody actually in our green room as yet. Nobody has logged in directly to the naturalphilosophy.org green room. So, and indeed, even worse, I don't have our speaker here yet. I've actually sent him an email, so I'll just check, is there any response? There are a few responses, so just give me a moment. I'll just see what they say. Yes, the speaker says he's there, but I don't see him logged in. So we'll just see what the situation is there. Let me see what the other people have said. Yeah, I think it may not have been updated. Goodness me, let me see. Can we do something about that? Let me see now. Yeah. Okay. So I'll have to try. I think people going into the link are getting a link to last fortnight's session or last week's session, which says it has ended. So I'll see, can I do something about that? Let me see now. I did the broadcast. I don't know what to do about that. Maybe I'll just give them a link to the current session. Copy that. Okay. So, okay. Right. Yes. Okay. Nick has come in through Facebook. Tell Eric to use the link to join the green room. Yes, I think I've done that. I'll just post. Let's see. Can I comments? No use. I've just posted the link to the comments. I'll just make sure that Eric has that, because nobody is here, including the speaker, as yet. So just give me a moment to check that. Wait a minute now. Okay, the speaker has come in, so let me just bring him up. Okay, Eric, at least you're there. Apologies for this messing around, and James is there as well, and Cornelius. So it's beginning to start. I omitted to update the link. I wasn't sure how to do that. We'll have to look at that. I had to do everything myself because David the Hillstar, I think, was out of circulation. He wasn't able to set the thing up, and we didn't know this. But anyway, the main thing is Eric is here. We have a number of sorry, Eric.
I'm here.
Great. We're actually recording at the moment. I've started the broadcast on time because I'm a little concerned. People seem to be in through the other media, maybe Dissident Science. Nick Percival has sent a comment in. So I think we can basically start without further ado, hoping maybe some people will join later. And anyway, the link I put up at least worked because you and Jim got in through it. I'll just check with Jim. Is everything all right? Is everything all right with you, Jim, just before we start?
Yes, I just received your email, and it's essential. All you have to do is click on that link on the first line, sir.
Great. I just wanted to make sure it worked. Thanks very much.
Yes, sir. Okay.
Okay. So it's confirmed that the link what I just did is the link from my creation of today's meeting. I just copied and pasted that into the email. So that obviously works now. Right. Harry, I think, has come in as well. Now, today, Eric will be speaking about the photoelectric and Compton effects without photons.
Right.
Okay, which is quite an interesting topic, because a few weeks ago we had a presentation by Henri Cornier, who I think was arguing for the centrality of using photons in all such analyses. He didn't go into details about the photoelectric or the Compton effects, but I certainly conventionally photons are used when analyzing these effects. In the Compton effect, for example, they're talking about a photon which is colliding with, say, an electron, some other elementary particle, and there's a reduction in energy and so on. So it'll be quite interesting to see what Eric has, because he's done a lot of
right.
experimental and an analytical work. So just to remind you what the spiel says. It says Eric will perform original derivations supported by physics' most famous experiments, and also supported by his own original experiments, which is important because many of us, actually, including myself, don't really have access to experimental experimental facilities in laboratories, since we're retired. But obviously, Eric has these. He's also going to give us an inner meaning of constants E and H. So the electronic charge and the Planck's constant. So they will be explored. Now, as usual, we'll give up to an hour. I don't know how long you want, Eric, but if it's 45 minutes, if it's 50 minutes, if it's 1 hour, 10 minutes, that's all fine. Something around an hour. And we'll then hand it over to the floor. There'll be a number of comments which will be coming in, I hope, because I'm a little concerned that not many are coming in on the social medias yet. But I have posted that link anyway, which is a main link to the green room, though. And then I'll bring people up in the green room. In fact, if anybody has anything to say, just wave your hand and I'll bring you up. But I'll bring you up anyway because I'd like your response to Eric's points. So and I'll be here. I'll get rid of myself, but I'll be here, Eric, in case there are any problems. And if anybody has some issue that they wish to put to Eric immediately, if it's a matter of clarification, we'll permit that. But we'd prefer if you keep your questions or comments until the end of the session, so we can deal with them in a more articulate way. Okay. So
is my pen board in focus?
Well,
I know it's very cluttered.
in focus, but it's a bit small.
Yeah. These are my notes mostly. Okay. I'm not expecting you to see all this. That's just my notes.
And people who are watching would be advised to maximize their own screens. I'll do that in a moment. I'm going to remove myself. No, I think it's all right. Certainly, there's some big blue type there, capital letters, and if you just point to them and say what it is, I think we should be all right.
Yeah, I'm going to draw things up new. These are my notes.
Okay. The one other thing is, in previous weeks, as you will have seen because you participated, we had people with PowerPoint slides, and we had two ways of putting them up. One was to sort of supply them to me and I could put them up, and another was to have them in here where I could put them up each individually. Have you any PowerPoint slides as well?
Yes, I have a whole pile of all that.
Okay. Well, the best thing, Eric, is I think to allow you to show them yourself when the time is appropriate, which means that you have to share the screen. We'll worry about that when the time comes. It'll only take a minute or two, but you'll probably see at the bottom banner in the center, present. You have to click on that, and then it'll say, what do you want to present? And you'll either present your slides. But we'll deal with that when the time arises. Is that okay?
Yeah.
Okay, so I'm going to leave you now, but I'll be here in the background in case you're needed.
Right.
So
well,
it's all yours now.
All right. Thank you. Oh, there we go. That's nice. Well, the photon is just about the most outrageous thing that ever happened. Let me try to explain what a photon is. I revert to Einstein's definition of the photon. I mean, people think it's a particle of light. That's only half of it. So the definition of the photon is pretty much the same as the experiment I do. It's that there's a way of making a one at a time. I'm going to skip that step, but there's a way to do that. And you have a beam splitter, and you have a detector at one side and another detector, and you put the signal together, and you put it to an oscilloscope, and you see if it goes one way or the other. That's the first half of the definition of a photon. A photon will go one way or the other. This way you get a click, or it'll go this way and get a click on the detector. The detectors make clicks. They make pulses. And I do that in my experiment. The other half of the definition is that if you were to reconverge the beam with mirrors, and then set it up like a Mach-Zehnder interferometer, and look over here and look for an interference pattern over time. So you get click, 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 click. The profile on a detection screen will make an interference pattern. So for any one of these clicks, it's going to have to go through both paths to add up to an interference pattern. And they all know that. So this is an AND system. It has to go AND both ways to generate this pattern. So right away, you have a contradiction. In this OR system, it has to go one way or the other. And the other way, it goes both ways. Like one way, if you look at this way, and both ways, if you look at it that way. That's the paradox. So that's important to know. Well, people try to make everything out of photons, but straight away, it's not understandable. And people have been trying to do it for 100 years. And what they end up with is acts of desperation, like many worlds, and we're on a computer simulation, and pilot waves, which I can show it doesn't work. Super determinism, it's all predicted. These acts of desperation and many worlds. Wait a minute, what's this? The photon is most people think, right, yeah, most people think it's going flying through space. They're not particles. It interferes. So that's the first step. It's like, where's all the weirdness come from? It comes from this idea of the definition of the photon. And this definition about both ways and one way is, it holds for matter and light. And let's see. I'm not sure if anyone has done the experiment. I'm the one who did the experiment for both matter and light. There may be other people who've done it since I did it. So I did my experiments as far back as year 2001, and did most of it ever since. So that's what the photon is. But I'm going to go all the way back in time to get some history of the theory as to how to resolve all this. And so if you look at the spectrum of hydrogen, you'll have the Balmer equation, the Rydberg equation, and Bohr's equation of the hydrogen atom spectrum. And there'd be a frequency is equal to some constant times 1 over n squared minus 1 over m squared. And you see that what that is, it's about a difference between two frequencies. So as soon as you do that, you'll understand beats. Difference frequency says it's made out of beats. Now, everybody else these days will put a Planck's constant on both sides and say, oh, it's about energy. More fundamentally speaking, it's about beats. And that's how actually Balmer wrote the equation. And so I was looking at this quite a bit, and to see who else talked this way. It turns out Schrodinger, in his first paper, explained charge in terms of beats and deep difference tones. A direct quote from his first famous paper. So, but that's about it. Hardly anybody uses this. But anyway, let's draw a picture of what that's about. And so what I found is that there's a way of fitting light to the beat. And so as soon as you have two frequencies, this one plus this one, different frequencies, you can use a trigonometric identity that says it's equal to a modulator wave, this envelope wave, times the average of the two frequencies. So this envelope wave is there straight away as soon as you do adding of two frequencies that are close together to make beats, and you subtract them. You subtract the equation of each frequency, and so you get that, which is what the spectrum of hydrogen tells you. So I'm assigning light to the modulator, and the inner wave is Schrodinger's psi. And if you do that, then you can derive a whole pile of physics, which is what I did. And so we'll go back to the de Broglie equation and the photoelectric effect equation. Let's look at the photoelectric effect first, because that started out a whole pile of physics, of quantum physics. Well, actually, I may want to just say, well, where did Planck's constant come from? People say, well, where are these constants? Planck's constant was so great. It's about a spectrum of energy versus frequency as a function of temperature, and he derived having to use this constant. And for temperature, it changes the curve, but it fit experiment is the point. By using Planck's, it didn't fit experiment until he used this great constant. And so, but the equation of the normal spectrum, as it's called, does not have the other constants that are used in the other equations. Like there are three constants that I like using: the charge constant, the amount of charge in an electron, the mass of the electron, and Planck's constant. I'm going to do a lot with those three numbers. And how they're related to experiment. They didn't come from nothing. They came from many experiments. So there's Planck's constant Planck's equation does not have the other two constants that I just wrote. So there's an independent way of getting that constant. That's an important part of my theory about what does the experiment say. Let's look at the experiment and say, what is the message of nature for each experiment? So let me just go back to the photoelectric effect equation. So Einstein did an original derivation of Planck's constant times frequency. Now, he didn't write it with h. He had several other constants that canceled out to make h, but we'll forgive him for that. And then he said, all right, well, that's a cool energy. Let's just do the photoelectric effect and say, well, what would it take to knock out an electron with this energy? And he just wrote down the kinetic energy that everybody uses, mass velocity squared over 2. That's the definition, the derivation that Einstein did for the photoelectric effect. It's not much of a derivation, but he did derive E equals h nu independently, his own way, from Planck. But he knew about Planck, how he did it. So they both came up with E equals h nu as something great, and it is great. But the derivation that he did is more of a statement of a postulate of quantum mechanics. But I'm going to show how to link this equation, which I call it a frequency equation, where I'm going to link it to a wavelength equation. The wavelength equation is the de Broglie equation. Well, how do you do that? Well, what's frequency is velocity over wavelength. So I'm going to just write that in there. But I'll do it for the matter wave, because velocity over wavelength. Then what? So now we can cancel out a v. So I'll do h over lambda equals mv over 2. All right, mv, that's momentum. But we have this factor of 2, okay? It doesn't quite work. This is very close to the de Broglie equation if you take away the 2. So how do you fix that? The way you fix that is going back to the beat thing that I just did and said, oh, there are 2 beats that fit light, that are in the interaction of light and charge. There's 2 beats for the modulator. The modulator wave is this part. So you go, the frequency of the beat is equal to 2 times the frequency of the light. Then you stick that in here, you stick it in back here, and you get to get rid of the factor of 2, and you get the de Broglie equation. And so the great thing about the de Broglie equation is that it fits experiments in diffracting matter waves. So the first time this was done was by G.P. Thomson and Davison and Germer. They did it about the same time, around 1925. And the better way to explain it is if I go a few years later to Esterman and Stern, who diffracted helium. So I'm going to draw the helium experiment. So you have helium in some oven, and you set up a toothed wheel where you have a hole in it and some other aperture with a hole. So you get to measure the velocity of the helium that comes through and sort the velocity that comes through. And then you have it going through a thin foil. And you know the spacing of the foil from X-ray diffraction and chemistry. And so you know this. So you set up a diffraction grating with helium, and then you can use the Fraunhofer diffraction, which is lambda is equal to d sine theta. So here's the theta. And so you measure that, and you get the wavelength. You get the d. This is the d here. There's a spacing that you know from other good experiments. It's not arbitrary at all. So you get the wavelength. And so you go back to this equation. You want to see, well, do you get the de Broglie equation? So you get H is equal to mv lambda. You can get it any way you want. So you put the wavelength in, you get the velocity, and then what else you have? Oh, you have this H to M. Let's put the M on the other side. The message of the experiment is the H to M ratio. You actually borrowed M from another experiment. I'll show you that experiment. And you borrowed H from the normal spectrum. So the same situation happens with electron diffraction. Maybe not as many things because you don't quite measure the V. You can get the V in another way. But anyway, the message of the experiment is really this constant. And so I'm going to look at, when you look at the de Broglie equation, well, this is the de Broglie equation. And we go back to the photoelectric effect equation. I'm going to write that. It's the same situation. What is the message of the experiment from the photoelectric equation? What is that? So you get Planck's constant times frequency is equal to mv squared over 2. There's another constant in there about escaping the electron potential. That could be added in later. Just from the inside, it's as simple as this. So the message of the experiment is, I'm going to rearrange it. Let's put the frequency down here and the mass down here. This is the experimental message of the photoelectric effect. You get this constant, the H to M ratio. Now, if you go back to history and see how Millikan did it, he'll say, oh, this is a way, another independent way of getting Planck's constant. It's not true. It's a way of getting the H to M ratio. So you have to borrow the M from another experiment. So I'll explain how that was done in history. And it all applies the same way now, whether it was a long time ago or not. It's still the same situation. First, J.J. Thomson did the charge to mass ratio experiment, which was completely great. He used the particle model. Now, the particle model has its place, but it's not always a particle. I'll get to that. But still, he deflected a beam of charge and used force equals mass on acceleration, and then he used, well, what's acceleration? 1/2 at squared, and then the Lorentz force. And this is all in books. So the Lorentz force is for balancing the deflection of the charge beam. So you get a deflection here, and then he straightens it out with a magnet on the whole thing, magnetic field going in and out, and then puts a whole bunch of terms together, and he ends up with an expression for the charge to mass ratio. He's looking at, he's using the particle model, and so there's a charge and a mass ratio, and so all the other terms are directly from the experiment. So you measure the charge to mass ratio, and then a few years later, in his lab, a fellow Townsend did it very similar to the Millikan oil drop experiment, where they'll weigh a charge in an electric field and an oil drop that has charges in it, and then they'll see how it moves. And very soon after, JJ himself did the same experiment, and say they were able to extract a number for the charge constant independent of the other constants. And that's important. No, I take it back. He got he got E. He got E, and then he put the E into the E to M ratio, and that's how they got the mass of the electron. So at this point, we're able to see how they got these three constants: the charge, the mass of the electron, and Planck's constant. And we get to see the message of the experiments, which experiments give the ratios and which experiments gives the independent numbers for these constants. The mass, you have to use a combination of two experiments to get the mass. But the Planck's constant can be independently extracted, and the charge constant is independently extracted. So where am I going with this? I'm saying there's a list of experiments. Let me put the list of experiments that I've been through here that have these ratios to see what's the message of the experiment. So there's the de Broglie. The de Broglie experiment has the H to M ratio. And also the photoelectric effect has the H to M ratio. You can write the photoelectric effect with electron volts, and you get the E to H ratio. And then there's the charge to mass ratio that I just did from J.J. Thomson's experiment. So in looking at the message from the experiment, I found that when you have beams, when you see wave effects, you don't see the individual E and M in that experiment. You see the ratios. So the insight I had was to understand that what's quantized in the experiments that show wave effects are the ratios. The H to M is quantized, the E to H is quantized, the E to M is quantized. You do not have to quantize the H and the M and the E in those experiments. If you do quantize it, you end up with wave particle duality and you're lost. You won't know what's going on. The way everybody has been for 100 years, and you'll invent parallel universes and stuff. But you don't have to. with I call it the ratio trick. But anyway, so with this construct of seeing when it's in waves, what's being expressed, that it's really the H to M ratio and E to H, these ratios, you get to see how the loading theory works. The loading theory was there before quantization. The history of quantum mechanics is, well, first, Leonard had a trigger hypothesis, and he talked about it loading up and then snapping and doing something. And Planck had a loading theory. So I was looking, well, who did this? Who understood physics without quantization? So what I'm trying to say here, let me backtrack a little. So we have these ratios. I'm going to do it this way. Let's say you have an electron that's just emitted, and there's this wave that's spread out. You say, oh, well, is it a particle or what? Take a cubic volume of this wave that starts, initially it's quantized. And the same with light. It'll come out with a burst. So I'm saying the quantization is an illusion of thresholds that happen in initial bursts and also when it reaches a threshold in absorption. So what I have is a theory of the electron that lets you see things that will be falsely interpreted as a particle, but they're really thresholds in the way the electron works. So here's an electron. It puts out a charge. It initially has a whole charge, a whole action, and a whole mass. You take a little piece of it and you say, oh, well, maybe it'll have a tenth of an E, and it'll have a tenth of action. And you see the tenths cancel out. So there's something that's conserved. The ratio is conserved in the wave. So when the ratios are conserved in the wave, then its identity can be transmitted and be picked up in reverse to load up at the absorber until it reaches full E, H, and M. So I figured out how to make the loading theory work. It's because Planck, Sommerfeld, Debye, and even Millikan were exploring this idea of a loading theory where it loads up. So Planck did this graph where here's time and energy going up. And he said, oh, it'll load up and then suddenly it'll go down. It'll be a release of energy. The Planck understood the loading theory in his paper of 1911. And Thomas Kuhn wrote a book about all of this great work Planck did. It's called Planck's second theory. So Planck kept working. He had a first theory was everything was quantized. The second theory was that it's continuous absorption, explosive emission. That's a quote from Planck. And so he understood that it did not have to be quantized. So this loading theory, once it's perfected, it gives a discontinuity that's sort of a subset of the loading theory. So you get to see how things act like the illusion of particles. But it lets you accumulate gradually, and then you can explain all the wave effects without the probability wave. So what happened was people did not understand the loading theory. Millikan tried out the loading theory. He did not like. He wrote that there must be something wrong with the photoelectric effect, but he found that the equation was right. He did the experiment; it worked perfectly, and he explored this loading theory in his paper on the photoelectric effect around 1915 or something. But he said it was terribly difficult to conceive. So he did not do the steps that I figured out about the ratios and the other two constants that would have those ratios. And to see that it's not just Planck's constant that has this threshold. So the way Planck did it is that his constant was about a maximum. And also Sommerfeld and Debye did it. So in a paper by Sommerfeld and Debye, they have H here, not H as a point on this vertical. So when action reaches a threshold, then things can drop. So they had it right, as that Planck's constant is really about a maximum of action, but you do not see the sub-threshold actions. And you might say, well, how do you know that? My experiment shows that. So that's some of the history as to how to handle. So let's see. I did the photoelectric effect. So the next thing that happened was the Compton effect. So you'll see in all your textbooks they use the particle model for the Compton effect. They have an X-ray, and they'll have just anything with charge in it, and they'll draw little particles and stuff. And there'd be an electron that comes out, and another X-ray that has a lower frequency. And they do conservation of momentum, and they'll go, well, the conservation of momentum equation fits the experiment. Therefore, maybe there's something right about the particle model. Well, yeah, there's something right about it, but can you do it with waves? It turns out there is a wave derivation in Compton's book. And so I'm fortunate enough that I was able to buy the books. And so X-rays in Theory and Experiment by one of the greatest books. That's a great book. And there's also Millikan's book. These are some of the greatest books around. Electrons, plus and minus, protons, photons, whatever. So you see how these people did the experiments and their arguments. So Compton, in his book, used Bragg diffraction. And so you have a grading of, so the way Compton originally did it, it was clumsy. It's in Compton and Allison's book. I'm not sure whether it was Compton or Allison or what, but it's in their book. And they set up a system let me draw it this way, where there's a system of planes of charge, and they set it up where there was to create these planes of charge was very artificial. It didn't work where you invent a backwards wave with relativity or something. But what I did by going to that beat model is to say the layers that we're diffracting off of with Bragg diffraction is intrinsic to charge. The identity of charge is the envelope of Schrodinger's psi. So I'll redraw it to where there are these beats and they're planes of beats, and there's going to be a wavelength for that, a distance. And the distance that you use straight away is the wavelength, the beat length of that's used in the de Broglie equation, except I modified the de Broglie equation slightly so it's the length of the beat and not the whole wave to make everything. If you do that, it makes all the other physics work, and you cannot tell the difference otherwise. So, so what is it? Lambda is equal to h over mv, and so this is the wavelength of the beat, the lambda beat, and so that's what all this mess is over here, where I'm doing the derivation of the Compton effect, and so I'm going to write the Bragg equation, which has a factor of 2 in it. So the wavelength of the light is equal to 2d sine theta over 2. So the light will go like this. It's an X-ray. And so this is the electron ray. So the electrons are going to be pushed that way, but they'll still have this grating. And so the X-ray will go through, but this X-ray is going to be downshifted because it moves away. So you get to use the Doppler shift equation. And so I don't think I should go through all this. It's in my work. It's in all my papers. So use the Bragg equation and the Doppler shift equation, which is what is it? Delta lambda. The change in wavelength is equal to the original wavelength of light and the ratio of the velocity to the speed of light, sine of theta over 2. So you glob these 3 equations together with simple algebra, and you get the same equation. You derive the equation of the Compton effect that fits experiment. So right away you get to see, oh, there's a way of getting the same result of the experiment. You do not need to use particles. And so that's an important clue. But it's not quite finished, because let me draw the equation. The equation for the Compton effect is delta lambda is equal to something like h over mc, and I think it's 1 minus cosine theta. Okay, is that right? H, that's right. So so in this equation and in the de Broglie equation and the photoelectric equation, you have these ratios. Here's the H to M ratio. The message of the experiment is the ratio. Like you get to measure the wavelength, you get to measure the angle, you know C from other experiments, good experiments. The result is a H to M ratio. So this is another case. So there's a whole list of experiments that I have where people have interpreted the experiment in terms of particles. Well, they'll write out the individual H to M as if that's what the experiment says, but it's not. The ratio is the message of the experiment. And when you do that, you get to see, well, it does not have to be a whole H or a whole M, I'm repeating myself, to make this work. You can have the charge wave smeared out, diffused, like I did with that little cube, so that the fractions of action per mass per any volume cancel out. And the ratio is still there. That's the most important thing of my theory, is to understand, well, what are these ratios and when are they seen in what experiments? And how can it be that it looks like particles are diffracting? The answer is particles are not diffracting. If you see interference and diffraction, it's waves. And then you say, oh, well, but the detector made clicks. It looks like a whole particle hit there. Well, what happened was what Planck said. It went to a threshold, and then suddenly reached a threshold and a whole electron was released, or some discontinuous event happened that made a click in our detectors to give the illusion that a particle hit there. See, the particle effect in these wave experiments are a property of charge reaching threshold H, E, and M. And so that's the theory. So I had all this theory ahead of time. And then I said, well, how do I prove it? You know, people don't care about theory. They want to say, oh, well, show me the data. Right. So I went back to Einstein's definition of the photon, where he said, oh, it'll go one way or another. And I knew that one way or the other part had to be wrong. That's the problem. It's like, well, why is it wrong? I'll show you why it's wrong. But let's just draw the experiment again. It's supposed to go this way, or come on, this way, go click. So here's how do you know it's one at a time to start with? So they do something that I could argue about, but it's better to show a much better way than they do to see that it's one HF emitted at a time. And I do it the way all the nuclear physicists do it. And everybody agrees. And so we set up the detectors where there's a radioisotope in the middle and there's a detector on each side. And you put it into a coincidence experiment. You know, you look on the oscilloscope and you look at the pulse and say, oh, this one makes a pulse. And does it make a pulse at the same time? Whatever. And so what happens is, if it's something, if it's a radioisotope that emits two, and a lot of them do, in coincidence, when it decays, it may put out something in various directions. The direction initially is arbitrary, but it's directional. And you can tell from this experiment that when a decay happens, that it's not a spherical wave that goes out. It's like a laser that's a pulse of light. but it's gamma rays. So these are gamma ray detectors, and a gamma ray detector is a crystal of sodium iodide in front of a photomultiplier tube, and we see that they have pulse height resolution. That's really important. So they're full pulses that are characteristic of this gamma ray. So you do a graph of time where the time between clicks, if it goes click, click, it'll make a time. So here's 0 nanoseconds, and here's plus nanoseconds and minus nanoseconds. And the other way, go click, click, and go. So go clickety, 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 click. Oh, if there's a lot that happened together, you build up a histogram and you'll see a peak. If it does a peak, then you know it emitted 2 at a time. Okay. If it does no peak, if it just looks like a bunch of random noise here in this time difference histogram that everybody does in the experiment, then you know it emits only 1 at a time. Okay. It just goes zing this way or that way. And so the timing in between them is random. And you get this profile. And you know it's 1 at a time source. Then you take the detectors and rearrange them. You do the same electronics, the same isotope. You say, oh, it only emitted 1 H nu at a time. And now I've done it where it looks like a beam splitter, but this experiment worked better to where you have a thin detector in front of a thick detector, and you have the radioisotope, and it goes in, and it'll go click, or it'll go click. Well, what if it goes together in time? And you go put it in this time difference histogram, and you go clickety, 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 boobity, 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 and it goes, wow, it makes a peak. Now, no one else has seen a peak in this time difference histogram with anything close to a 1 at a time source, except me, because I knew what I was doing. And it means that something with 1 H nu at a time, an HF frequency, made 2 HFs here. Now you may think, oh, well, maybe you're looking at half height photons. Everybody says that. So the experiment relies on pulse height resolution, to where if you do a graph of the height versus how many happen just in a singles rate. So for a photomultiplier tube, it's just too wide. You cannot do the experiment the way everybody else does with a photomultiplier tube. You get a pulse height distribution like that. And you say, well, how am I going to set my discriminators? The discriminator is a filter that says, we're going to just start looking and counting pulses when they're this high. And then it reads, well, do you have coincidences or not? Well, where are you going to set it? If you set it too low, then you're not fair to the particle theory. And so there's a whole argument that I have, and it's better if you read it because it gets confusing. If you set it too high, you're not fair to the other theory. So it's not possible to do it, to say that you're not looking at half height pulses with something so wide. So with gamma rays, you get a nice peak where you know that if you set the discriminator that counts here, you're not looking at half height pulses. You're looking at full pulse. So other experiments where they actually diffracted gamma rays on crystals and got the deflection and used the Bragg equation and wavelength and frequency, and they're able to equate it to see, well, what is the energy? What is the H news of all this? So the height is proportional to the electromagnetic frequency, which is also proportional to what they call the photon energy, which is like in electron volts. That's all proportional on this graph. So you know that you're dealing with full H news here when you're reading it with a gamma ray. But you can't make the argument about, well, are you doing it fair to both the loading theory and also to the photon model, unless you use gamma rays. That's the only fair way to do it. And that's my discovery also. All this is my discovery that I've said. Oh, yeah, well, the new derivation. So, so you have these full height pulses, and you go, well, it's like 2 for 1. And so now I've done it where it really did look like a beam splitter as well, where I had a detector behind here and a detector here. And so here's the gamma ray source, a 1 at a time source. And I compare to chance, the chance of going to 2 together. And it's in the literature about this comparing to chance in this experiment. This experiment has been done before in the late 1950s, and Clauser did it, and Aspey did it. And they're the ones who won the Nobel Prize for entanglement. So they did this experiment, but they did it with visible light. And there are a few other things wrong with doing it with visible light. The beam splitter will polarize the light. And so it'll actually route the light to go one way or the other. And then there's another property of the detectors where it has dead time. So there are 3 problems I've figured out. There's no pulse height resolution, it has dead time, and just about any optics you use, even fiber optics, will route the light one way or the other and make it look like it went one way or the other in this kind of experiment. So they didn't do it right. So, and they compare to chance when they do this, coincidences, and they see chance. So the data that everybody bases this, the probability wave, where it goes one way or the other, is a bunch of noise. And so, how could they build up a whole physics on that? I don't know, but they did. It's just noise, where there are no coincidences, and they say, oh, it's random in this here 0 time. It's a delta time graph, okay, that I tried to explain. It goes click, click, click. If it goes together in time, it make a peak. No peak when they do it, this beam split experiment. When I do it, and so we compare to chance. The chance equation is pretty straightforward. You look at the singles rates, how many, so the rate of chance is equal to the rate in detector 1 and the rate in detector 2 times the time window within which we're counting coincidences. So it's a time window. So back to this experiment with, so if you see a peak here in this delta t graph, there's a time window here. And so that's the tau. That's the time here. So it's something under 100 nanoseconds, which you just set. You look at this graph and you say, oh, well, that's a nice place. Let's count those, the experimental rate of coincidences within this time window, and then compare that rate to chance. So the experimental rate, that'll be, I'll just put R sub E. So the experimental rate gets a number per sub counts per second. The chance rate gets a number of counts per second using the same tau in both cases. And that's how they do it. So I'm playing by their rules, by comparing to chance and seeing, well, do we break chance? And then I look at the ratio. So the ratio of the experiment count rate to the ratio of the chance count rate. And quantum mechanics says this should equal 1. It's just be chance, same thing. Now, I'm the only one who defies this idea of quantum mechanics. And I've seen numbers, depending on how you do it, incredible numbers. I hardly want to say it, like hundreds of times chance. But when I do it the same way, it comes out the same way each time. But there's all different ways to do it. So, I've done it a whole list of ways to say, well, am I defying quantum mechanics in a special case? Let me backtrack a little. I'm getting 2 for 1. Let me just review. How do I get 2 for 1? If you're thinking like a particle, if you're combining the idea of energy conservation with energy quantization, you get in trouble. So I'm saying you can have energy conservation in a general way where it's not quantized, and say, all right, you have 1 h nu here and you get 2 h nus. How do you get 2 for 1? And the way you get it is by what I showed before with the loading theory, that there's something there ahead of time. The action, charge, and mass is in this charge wave. But the charge wave is not full. It could be less, and it builds up until it's a full H of action in that beat. And so it could be a preloaded, partially loaded beat, which is the identity of charge. It gets light added in to give it more kinetic energy, and more. If you're doing a charge diffraction experiment, you'll have more charge. With light, you just adding kinetic energy to the beat. So if with gamma ray, that's light. So it's about understanding a preloaded state that Planck understood, and Sommerfeld and Debye and even Millikan understood. Well, they partially understood it. They didn't have all the rest of this detail, but they discussed it, that there is a preloaded state. So by getting 2 h nus at a time greater than chance, when you start with 1, 2 for 1, it forces the idea that there's a preloaded state. Otherwise, you're just getting energy from nothing. And so we embrace energy conservation, but we're showing that energy is not always quantized in this experiment. That substantiates the all this other stuff I was doing, where It's a ratios that are spread across space and diffracting and so on. So I'm going to quickly uh, uh, I can go through a few of the experiments, and there are other parts of my theory that I've done this to. I mean, I've applied this theory to spin, where I can see that there's a counter rotating psi wave, and there's this factor of 2. There's this G factor where I derived, and you can see it's about that it's going in both ways. So I handled spin, and maybe in another lecture I'll do that. I'll handle what spin is and what. So that's about the intrinsic angular momentum.
I think indeed, Eric, if I may just say quickly, we probably would be interested in hearing a bit more about your experiments now, because there's only maybe 10 minutes or so left. And we might ask you back, on a subsequent occasion to go a bit more into the
good.
analysis.
I was just going to mention that I handled a few other experiments. I handled antimatter. How is it that happens? The identity of antimatter, how they cancel, and the Stern-Gerlach experiment. But anyway, in the beam split coincidence experiment, so I did it with different detectors. There's a high purity germanium liquid nitrogen cooled detector, and there's 3 or 4 different detectors I used, and there's 3 or 4 different radioisotopes that I used. So there's a curious thing of like, why wasn't this understood ahead of time? So if you look at the absorption of the sodium iodide crystal, the absorption versus electron volts or frequency. If you look at that graph of the detector, you'll see that other people have worked out where there's a photoelectric effect. I think I have it backwards. There's a photoelectric effect. There's a Compton effect, and like there's the radioisotopes that I used are here. It turns out that I call it the unquantum effect. If you get 2 for 1 in this experiment, that gets better than chance. I call it the unquantum effect. The radioisotopes that I use have the photoelectric effect dominating over the Compton effect on this graph that I discovered. And so it makes it work better, and you'll see it. So this is cadmium-109, some radioisotope, and this is cobalt-57. And so I did a lot of work with these 2 radioisotopes that I emit only one at a time, as known from that true coincidence experiment with sandwiching in between. And so many of the books, they'll look over here at this other isotope and they'll say, well, what happens there? You can do the unquantum effect with only one detector. And you would have thought that they would see this if you just do one detector. If you have one detector, if it can split into 2 detectors, it should be able to split into 2 in one detector, like inside. So you'll have one emitted, and then here it'll make 2. You'd think, well, so you should see that. So if that happens on the pulse height spectrum, gamma ray spectroscopy, if you do gamma ray spectroscopy, and that's what you have to do in the beginning of this experiment. So you look at electron volts, which is proportional to the electromagnetic frequency. and the pulse height. So you'll see, oh, well, cadmium 109 makes a pulse, a spectrum. And then, so that's at the characteristic pulse height. Well, what happens at where it's twice as big? If it's twice as big, you'll see it's called a sum peak. And I've done it. You can calculate, well, how many happen here? And does the number here where there's 2, does that equal chance? And it usually does. And but I found where I was able to see, actually I did my best where it was with the cobalt 57 with the other isotope, where I was able to see an anomalously high sum peak here, which ended up being twice chance. So you can see the unquantum effect with just one detector and just look at the spectrum and do some calculations on it. It turns out you need to use the detector that you think is worse to see this, which is a sodium iodide. And everybody else uses the one that you cool with liquid nitrogen, which gets better pulse height resolution. It comes out with these nice narrow peaks. And I've used that, and I can see the unquantum effect with that also. But the sum peak doesn't come out as big, and it looked like about chance because the photoelectric effect efficiency for that frequency gamma ray turns out to be close to the Compton effect, and the unquantum effect is about the photoelectric effect. So maybe I'm getting too complicated here, but I sorted out why is it that other people have not seen this effect. It depends on which gamma ray you use, which detector you use, how you set it up. And so I had a good idea of how to do that because I knew what was going on ahead of time. And that the photoelectric effect would be the thing to look for. So I did set it up where I look for this 2-for-1 effect where there was a thin detector in front of a thick detector, and this one was liquid nitrogen cooled, and I was able to see this bigger. Well, I did it with 2 different kinds of detectors with different results, where some of the experiments were with sodium iodide and some of them with high purity germanium, which is the liquid nitrogen cooled detector. And so there can be 2 here. It could be 1 here. So it splits in 2. There could be 2 here. If it can split into 2, it should be able to split into 3. Why not 4? Why not more? I've seen it. I've seen where it goes even here. I've done experiments where I can see that there are, I call it the ×2 peak and the ×3 peak in the spectrum. So I do coincidence triggered pulse heights, but where this triggers, so it's an unquantum effect where it causes both this in coincidence with this detector. And then I look at the spectrum of this detector to get to see all this. So there are all these variations of the experiments that I've done. That's one of them. Another one is, well, what happens with distance if it's really a classical gamma ray, it comes out with some cone, and I found that the distance from the source to the detector matters, where the atom size has to fit this cone. And so I did calculations on these experiments with classical theory of waves, how much it should spread sideways and to fit the atomic absorber. And so I found distance matters. And then I found I did some real interesting effects where the beam splitter was in a magnetic field, and it would split. And depending on whether it was carbon or a ferrite, it would split it. You'd see signatures of whether it had a Compton part of the spectrum or a Rayleigh part. You get to see signatures in the pulse height coincidence spectrum. So I was able to see the structure of charge. I made all these discoveries with this on quantum effect. I kept doing it in different experiments. And so the chemical state of the source mattered, whether it was I actually electroplated cadmium 109 to make a metal. So I was able to see how chemistry influenced the gamma ray structure. And one of the more, and then there was, could I do the equivalent of X-ray diffraction crystallography with gamma rays? So you have a crystal with spacing on it, you have gamma rays, and so here's a detector, and here's a detector. And so you have my one at a time source, the gamma source, gamma. And so I looked at the quantum effect here, and then so I get a number for what's the ratio above chance. And then I rotate the crystal, okay? And so that should deflect it differently. And I saw that. So I was able to see a diffraction effect light up with the quantum effect. So this is an invention. I call it photon violation spectroscopy. I put all of this information in a patent application around, I don't know, 2003 when I did this, all these experiments. I gave them 20 experiments worth of data as to how to use the quantum effect to see crystallography and the structure of the charge in different states. And it was obviously useful for material science. And they just treated me like garbage and hardly looked past the title. And so, but it's still there on the internet where you can see I did it. It dates my work. Filing a patent is like publishing. So one of my earliest publications are these patent applications. And so one more really important thing. It's not just for light that does the quantum effect. So there are two detectors I have. I split the alpha, the helium nuclear matter wave. So you have some americium. You take apart a smoke detector, you get this radioisotope that puts out the alpha ray. You use a thin foil of gold, and you see it's very similar to the way Rutherford did his model of the atom, where he took alpha rays, and well, some of the alphas will go through the gold, and some will reflect off the gold. But can you split the alpha like a wave? No one else would try that. So he did the same circuit with the coincidence experiment and all that. And so what I did is at first I looked at half height pulses, and you go back to, well, what does it take to split the alpha? You look at other experiments where they did collisions. It takes 7 MeV per nucleon. It takes 14 million electron volts to split the alpha into 2 deuterons. And you might think, well, maybe I'm looking at 2 deuterons, but I don't have enough kinetic energy. There's only 5.5 MeV to start with. I don't have the 14 MeV to split the alpha into 2 deuterons. So anyway, when I did this and I looked at half-height pulses, I do 105 times greater than accidental chance. So I'm doing something completely different by defying the binding energy calculation. But then I look at, well, what's the full height pulses? And so I did a lot of work to put this on a two-dimensional graph where I look at the pulse height in coincidence of each event. And you'll see it on my papers that I published this. And the full height pulses, and they're all perfect pulses. It's like it's almost 6 times chance. Now, that's a sensational thing. It should only be chance that it goes one way or the other.
I'm always reluctant to do this. You must pardon me, Eric, but if you could perhaps finish up in the next few minutes,
I'm
because
done.
we want to give a bit of time for discussion. I hate interrupting you because it's all fascinating.
Yeah.
But if we could do that, that would be great.
Yeah, I got through the important part.
Excellent.
It's that I resolved wave particle duality for both matter and light with these sets of experiments, many experiments, and a theory to go behind it, and an understanding of what happened in history to make people think that it's a probability wave or particle probability model, and what assumptions are along the way. So it's all written up in various papers. I'm ready for questions.
Excellent. Well, thank you very much for being so comprehensive and understanding of the limited time we have available. I just, there are a couple of questions here, and perhaps we could put them to you. And also, I'd like to bring in maybe a couple of people from the green room. But just maybe some preliminary comments just to set the ball rolling. Actually, I was interested in your statement, which I sort of wasn't aware of, that Einstein had effectively, independently, maybe in other terms, introduced the basic quantum equation. I thought he was just borrowing from Planck's work at the beginning of the 20th century. You've also mentioned Debye and so on, who independently, I suppose, did work which was similar to Compton's. And in fact, I think it was important, that you had gone to the original texts of people like Compton and Millikan. Right. The books you showed. Too many people, dissidents, but mainly mainstream people, are just happy to read secondhand accounts of what A, B, and C have done. Yeah. And I think that's part of the problem with modern physics.
Look, this was a major effort to get the books and papers.
Yeah, you've got a big library there. Yeah.
Right.
Actually, it just brings me to the other point. I have one or two other points. So your publications, have you published? You have a website, you say. Yeah. Have you published in any particular, systems or Galilean electronics or maybe the
progress in physics. Progress in physics and physics essays.
Physics essays, yes.
And I'm about to be published in the Journal of Modern Physics. They invited me to publish in a special issue on entanglement. So that's what's going to come up soon. But all of this, and there are other publications also. It's all on thresholdmodel.com.
So that's your website, which you had in blue writing there.
Right.
Thresholdmodel.com. So I think a lot of people will be interested in having a look at that.
And there's video.
The invitation to publish is in contradistinction to your bad experience with the patent application, with on quantum effect and so on. But unfortunately, one must say, not surprising.
Right.
Anything new is looked on askance, unfortunately.
I was invited to publish in physics essays also.
Okay. They're fundamental publication, which they tend to look at new aspects.
The editor is an expert in this wave particle duality stuff. I went to a conference called something like "What Are Photons?" Back in 1914 in SPIE engineering, a big conference. So I attended this conference and submitted a paper with them as well. So I have 4 or 5 publications, but they're not big time names where it's published. So, but this next one may be better. People will be able to look it up.
Okay, and actually, people will be interested in looking at the recording of this session. But is this too simplistic? I mean, we have one comment here that Rita's idea is that there is only electromagnetic waves and fields instead of particles. Would that be a summary, or is it too simplistic?
That's good. Light is just an electromagnetic wave. It's emitted in a burst, but thereafter spreads classically. So light is always a wave. There's nothing particle-like about it. It's the way light interacts with charge that gives the illusion of particles. We only know light through the interaction of charge. And also, the only other exception is pair creation and annihilation. But that only happens up at millions of electron volts.
Okay. And Roger Anderson just said waves made out of particles. So he's maybe trying to save it.
People try to do that, but what's your weird on particle detector? There's no other particle to detect, and you have to start making stuff up. Where how do you do the true coincidence test? We only know physics through these clicks and a combination of many experiments. So when you look at the combination, it becomes clear. So many people have tried. I've seen that where they try to make waves of particles like that.
Okay. Anything else? I'm just looking at the comments before I maybe ask people in the green room would they like to come in. Cornelius is saying, well, he's responding to Roger in a way, but he's saying, I see particles as focused wave patterns in the continuous ether. That might be one way of looking at it. I think so.
Well, they're not going to diffract. You go back to Esterman and Stern and see, well, how is it that helium made a diffraction pattern? Oh, and then my experiment where I split the atom as a wave. How do you explain these 2-for-1 effects with particles? It just breaks down to do it any other way.
Right. With his wave model, particles be more like plasma, he says. So we get waves in them too.
Yeah.
It's the same man who made the earlier comment we referred to. Okay, let me see anything else. See, a lot of this is just discussions between the people participating in the social media.
So it's 100-year-old paradox. Many have tried, and they are shot down not just by me, other people, where it doesn't fit the combination of experiments to try to make wave effect, to make particle effects at different ways. They end up, the most common model is shut up and calculate. Like there's no model. It just seems to work that way by our experiments. And then there's other acts of desperation like came up. And
so, even logically, where we have sort of things simultaneously being one thing and the other, depending upon what is more convenient, there must be something wrong where we have to resort to that sort of...
right. Well,
okay.
I claim to have figured it all. I figured it out. Nobody has defied the strong prediction from quantum mechanics in this beam split coincidence experiment. And then there's the two particle experiment. So the beam split experiment, I call it the one particle experiment, but there's also the two particle. I kind of in fun, I call it the two particle experiment. So the same people, Aspe and Clauser, that did the one particle experiment, did the two particle experiment. The two particle experiment is what's famous for entanglement, where you have two H news going in opposite directions, and you have a detector, and you'll have polarizers, and you look for whether it's sideways or up and down or the other way, and then you'll compare it, and you put together a graph of the angle of the polarizer on this part of the graph, and you'll do how many coincidences, and you'll end up with Malice's law. And so you put together, well, what's the relationship? So it's confusing because in this case, when you do the two particle experiment, the experiment and quantum mechanics agree. And it also agrees with classical mechanics, Malice's law, and it also agrees with the threshold model of me. What does not agree and has everybody all bent out of shape is Bell's theorem. Bell's theorem has some assumptions in it where it's not a curve, it's a straight line here. And they'll do experiments near where it's different. And they'll say, oh, it violates Bell's theorem. And so then they'll say, quantum mechanics is non-local, it's weird, and the universe is weird because it violates Bell's theorem.
Yeah, the
So,
inequality.
What?
The inequality, yes.
Yeah, right. So the terms in Bell's theorem, they're just all linear. There's no sines or cosines or anything. So it describes a straight line, whatever's behind it. And people have drawn this graph.
Maybe I might be reverting to the people in the green room just for a bit of a discussion, but just one final point. Would you have any comment on this almost final question that's been put up? Could it be that the particle is a standing wave?
Yeah. It's in the atom, it's a standing wave. There are a few different ways it's a standing wave. And
okay.
I also did a derivation. I did my own derivation of Planck's black body equation, where I did it with beats and standing waves and
right.
put it all together that way. So yeah, it's a standing wave in the atom. When there is such a thing as a particle, it's a two-state system, and there are a few other experiments where you can sort this out. There's an experiment. There's a very interesting experiment done by somebody else in around 1999, where they diffracted helium, and it won't quite go straight through by itself. It has to focus. They get a focus through a diffraction grating. And so if you look here, you get a big peak. And then here, there's going to be a plateau where it goes straight through. So you can see the signature of particles in this diffraction experiment. They don't all diffract. There's a signature of it in the particle state, and there's a signature in the focusing wave state. And they say it. They say that the experimenters explain that this is the wave function of helium making this peak, and that this is like a shadow pattern. So you get to see the two states of the atom, that it can have those two states. But they can still interpret this focusing with the probability wave. And then if you look at my experiment that defies the probability wave, then you get to see what's happening, that it's a loading to a threshold where the wave is actually going across a physical wave of helium with those conserved ratios that that can show itself in this peak. So I put that in
Very
my.
well. Well, is there anybody in the green room who'd like to come in and have a brief word with Eric? I see we have Jim, we have Cornelius is signaling. I'm going to bring you up now. We have to unmute you though. Cornelius, unmute yourself. Fine.
Okay. All right. Can you hear me okay?
Yes, I can hear you.
Okay.
I think we can all hear you.
Well, one thing that Eric said is that, that particles are standing waves, and I agree with that. He also said he did interference patterns between particles, and if particles are standing waves, then he basically did interference and diffraction of standing waves or waves. And so light being, if light is in fact a wave pulse, then wave pulses would also interfere with standing waves, which would mean that the wave pulses of light would diffract as they encountered the wave pulses of matter. And so waves do diffract. The wave crests will synchronize with other wave crests that are nearby and will basically be entrained by other waves if they travel together long enough. And that can be seen as simple ripples in the ocean become large waves because the ripples become additive as the peaks of the smaller ripples attract each other and become larger and larger waves. So waves do in fact entrain each other, and waves can in fact be diffracted by other wave patterns. So if light is a wave and matter is a wave, then the entire thing kind of falls together.
Well,
that's my take on it.
Just look at my derivations of the photoelectric effect and the Compton effect. And so what solidifies the way I do it is that there are envelopes, there are beats or standing waves that the light will diffract off of. The layers, there has to be layers of something to diffract off of. And so I make beats of charge. And that's in the derivation of the Compton effect, where I try to explain it. You use the diffraction equation. And so there's these layers, the layers of charge, which are made out of envelopes. You could draw these beats here, and you have light that interacts, and the equations work out. Similarly for the photoelectric effect and the de Broglie equation. So yes, you don't need particles for any of those experiments. I outlined the derivations of those experiments. And I expect there will be plenty of other experiments that will be able to be treated the same way. And so you can do that.
Right, it's an interesting conception, and I think we're not a million miles away from each other. Actually, in looking at these things, is that okay, Cornelius? So yeah, thanks for your.
I think that's perfectly. We're basically in agreement that particles are waves, and waves are really interacting with waves.
Okay.
There's still such a thing as a particle, though. There's a particle state. I mean, there's still a way that it holds itself together. So if you look at the equations of, let's say, the hydrogen atom or such, those ratios that I pointed out before will come out with different powers. If you see other powers that don't just cancel out in that simple way I showed, those are equations that show how the waves hold themselves together. There is such a thing as a particle. But when you have equations and experiments where it smears out and you see just the wave effect, you'll see these simple ratios, the H to E, the E to M, and what is it, H to M ratio in the equations about the experiments that show wave properties. And like in the Lorentz force has that. That's another one. So there are all these equations that have to do with beams and wave effects. You have these ratios. So that's
Right.
how you can
Dependent
tell,
on each other.
looking at the equations, if it has different powers, like the equation for a black body spectrum doesn't have these simple ratios in it. That'll be about how it holds itself together as a particle. You can tell by the structure of the equation.
Anybody else in the green room wants to come in? We have Jim. We have gentleman Chasm, who doesn't seem to have a video, but he's in, and we also have Jim Morrison, James Keane and Jim Morrison. If I call you both Jim, we'll be confused. So I think James is coming up. I'll bring you in now. You probably have to mute yourself, or I'll have to do it.
Hello,
You've done it.
thank you, Eric, for a wonderful presentation, sir. I really appreciate it. I wanted to ask you what you think about the vacuum, because in your 2-for-1 experiments, and you're talking about a preloaded states and the idea of loading, how does this relate to talk about virtual particles, or the fact that, at least in my work, the vacuum is not empty, that it does contain a lot of energy content?
Well, there's a lot there. I'm not dealing with special relativity. I mean, the closest I get to special relativity is to say that the inner wave that I assigned to Schrodinger's psi, that it will travel at the speed of light. And so it's there, and there are envelopes of it all over space, and that the identity of what's it called, where you have what's that preloaded state called? 0 point energy. The identity of 0 point energy is that the envelopes of the psi wave are sub-threshold. When you get it, there could be an envelopes of psi wave that are all over space, and they may not even be making envelopes. They'll just be psi waves. But there'll be a maximum where it gets to be h as the area of the envelope, Planck's constant, and then it'll start acting like a particle, charges running around. So yeah, the vacuum has this preloaded, this 0 point energy all over it, where there's charge waves running around and electromagnetic fields. That's as close as I get.
If you're in your 2-for-1 experiments, which I think are brilliant, I'm wondering if you could just explain to us. It seems to me that something was already there in the vicinity of the detector, and so that when you have the energy content of your gamma ray coming through, and you get 2-for-1, in order to get 2-for-1, somehow part of the energy of your original gamma must combine with the energy in, let's call it the vacuum, or whatever, in space. I was just wondering how you think about this. If energy is to be conserved, how, what is this? In other words, I'm saying something seems to be already there near the detectors.
Already there. It's in the matter of the detector. There are preloaded states. There's noise running around, and thermal energy of all kinds. And it may not take very much to reach the threshold. And so that's why it doesn't happen all the time. If there could be a preloaded state that's close to a threshold, you just don't see it. It's in the matter. It's in the detector already. It's in the charge waves. It's already in the charge. There's states of charge there in the detector. And it just takes a small amount extra to trip it off with this shock wave of gamma that that will set it off. So there are other
Okay, thank
experiments.
you. You know, like I think you've clarified that. You're
Yeah.
what you're calling it is preloaded states, and so lastly, you would then say that there really is a conservation of energy in your 2-for-1 experiments.
Well, sure.
Okay, thank you, thank you. I appreciate that, sir.
Okay, and thanks very much for those comments, Jim. So I'll just check. Is there anybody else who'd like to come in? Jim Morrison, did you put your hand up? Any ideas? I'll bring you up anyway, just in case you have any response to some of the ideas there.
Hi. I'm wondering, have you ever heard of Peter Beckman and
No.
Einstein plus two? His book,
No.
Einstein plus two. He had a very, sorry?
No, I'm just surprised because I'm not knowledgeable about all these things. I thought you would have heard of him. Yes.
Yeah, he had a derivation of what I consider to be the wave nature of matter. Okay. Essentially that if you assume that there is let's say you call it a preferred reference frame, and you've got an electron and you're shooting it out of a beam, that it experiences Lenz's law, which essentially will cause it to slow down, and then it will generate magnetic fields and electric fields, and as they collapse back onto the fields as it slows down, the electron gets accelerated. And what you have is essentially a sinusoidal variation in velocity and I guess energy on top of the average velocity of the particle. So, and that's essentially what is the wave nature of particles. There's the real particles, and they have mass. You didn't talk much about mass, but these magnetic fields that are spherically essentially emitted, and electric fields cause this acceleration and deceleration of the particle. It's a small perturbation on top of the average velocity. Now, for example, if you shoot your electron beam at a diffraction pattern, and you see the interference patterns on your photodetector, that it's actually the magnetic fields that the interference of magnetic and electric fields that guide the particles to the interference pattern.
All right. Let me just say
similar to Bohm's idea of guiding waves, but actual physical waves.
Yeah. Well, look, this business about diffracting particles, like people always use a double slit or a single slit or whatever. Let's just look at a double slit. Let me just say something really simple about that when you're diffracting. And they try to say, oh, well, we have a diffraction pattern. Okay. Well, that's kind of a problem, but it's much worse than that. It's that if something happens here, it eliminates, according to quantum mechanics, and if you think it's a particle, that it'll happen any place else. Okay, that's the real paradox of quantum mechanics. So if you're not looking at this effect that's much more profound, you're just saying, oh, well, there's wave properties and particle properties. Well, we know that. We know there's wave properties. This is the real problem that it eliminates. So the experiment to sort that out is the beam split coincidence experiment. And then you get to say, well, for all these different paths, we're not going to worry about all of them. We're just going to look at two paths and say, well, does it do this or that? And that's how you sort out the problem. I mean, I did not really understand what you said, but it looked like you were just diffracting electrons and you're seeing wave properties. That's nice. We know about wave properties, but you can still reason that out with probability or something else, but you're not going to sort out whether it's a whole electron that you start with and whether you get a whole electron this way or that way. I didn't do it with an electron. I did it with helium. I actually did it with a matter wave of helium here to see, does it go one way or another at a beam splitter? And so that's where you get to the heart of wave particle duality. And I found that you can split the atom that way.
It's certainly interesting discussing all these aspects and speculating on them, looking at them from different angles. Now, before summarizing and finishing off, I'd just like to check very briefly. We have one person new, I think, to our green room who doesn't seem to have a video, but I'm going to add him to the stream. Kazim Moflahi, I hope I'm pronouncing your name correctly. You need to unmute your mic. Maybe you're not able to do that. I don't think I can. I don't seem to be able to do it. Unmute mic. Okay. Well, you no doubt have heard the lecture and you've heard the discussion. So and you can look at the Threshold website, and if you have any further comments, you can come back to us on that.
Right. Thresholdmodel.com.
Thresholdmodel.com. Okay, very good. Well, I'll take him down now, and we'll be interested. So I'd just like to thank everybody for participating, all your comments and discussions, and in particular, I think we owe a debt of gratitude to Eric for having gone to such trouble to explain to us the basis behind his work in regard to dispensing with the fundamental concept of the photon, I suppose, in regard to these electromagnetic wave analyses and considerations in regard to applications to things like crystallography and so on, and the various experiments that he's done, very fundamental experiments. He reminds me actually in some ways of like an 18th century or 19th century scientist who works alone and has all the both the experiment and the theory. I think actually a lot of us dissidents could be considered somewhat in that category, because nowadays, unfortunately, the fundamental experiments are all done in teams, and you have experimentalists, and you have on the one hand, and you have theoreticians on the other hand, and they both have their own ideas. But the spokesman of the organization is maybe the chairman or the chief executive of the team, and he decides what people are allowed to say. It's almost like a sort of a censorship. And you're getting, oh, the team thought this, and this is, you're suspicious that there's actually maybe financial incentives in there and PR considerations, and maybe considering about their next project, and maybe whether they're going to get support on the basis of the results coming out of this project. So when I hear somebody like Eric speak, and when I hear many of our other dissident people speak, I don't see any of that in it. It's really the disinterested pursuit of truth, which is really what science should be all about. And we can agree with a lot of the views expressed today. We can disagree. We can think they're one way of looking at things. They're partially true, but it gives us a lot of food for thought. And I'm very happy that we've had Eric today. And in fact, I think on a subsequent occasion we may ask him to come back in regard to particularly the developments in his work. We give him he give us an update on a subsequent occasion. So again, just once more, apologies for the slight hiccup today in announcing the lecture, and maybe having to give you a direct link to it because it wasn't automatically updated. We'll try to sort that out with David de Hilster for the next time. The provisional plan would be next week. He would be hosting a general meeting, and maybe in 2 weeks' time, we'd have a further alternative session, technical session. And I think we have a few. We have about 3 speakers in the line. Excuse me, for over the next few weeks. And if you have any ideas about what you'd like us to maybe have a lecture on, please just pop a note to us in the CNPS, and we'll have a look at that, and we'll be very happy. So it's time now. The time has just elapsed, so we must terminate. But thank you all very, very much for participating. Thank you for the questions. Thank you for discussion. Thanks for everybody in the green room, and most particularly thanks to Eric for having gone to all this trouble, as I say, to give us the lecture in a very short period of time. You know, we only have maximum maybe an hour and a half to discuss the subject if we want to give a reasonable time for questions. So he managed to do that, and thank you very much. I'm going to end the broadcast now, and we'll meet again in the not too distant future. So wherever you are in the world, I'll just say good day rather than good morning or good afternoon or good evening. Good day to everybody, and thank you again.